Hello everybody, this is the final exam review for Stats 309. I'll be walking through some suggestions first. So I suggest that you work problems from your textbook, work in groups, perhaps with the people in plus, review what I've learned at each chapter, review all your midterm problems as those will be representative of the kinds of questions you will see on the final. You can bring 3 pages front and back of notes, and you should definitely work the sample final exam. Don't cram and stay up all night. Try to start studying now, today if possible. Also, Dr. Greenberg made this PowerPoint, so I would like to thank her for that. My suggestion for working the final exam, you might find a way that works for you and do whatever you think is best, but personally, I like to wait until I've made the notes and I've studied everything and then take it maybe a day or 2 days or whenever I feel I'm truly prepared before the exam. I take it and then see which knowledge gaps I still have. Here are some things you need to bring to the exam: your 3 pages of notes, your ID, your pencils. You can't have a calculator, a phone, anything like this, but you will have everything you've had on the past test. You'll have you'll have the R help pages, and you'll have blank paper. So 50% new material, 50% material that's been on test 1 and 2, and it's a 2-hour exam. If you're going to read the textbook to study, skip these sections. We'll jump right into the test 1 material. So data, variables and cases. Variables can be categorical or quantitative, and quantitative data can be nominal or ordinal. Data can be cross-sectional or time series. Distributions describe the values of the variable and how often they occur. Listed in orange on this PowerPoint are the R commands you use to make certain things. So for categorical variables, you can use any of these plots. You can use plot, pie, table, prop.table, margin.table, bar plot, and mosaic plot. For quantitative, you're going to want to use histogram, stem plots, time series plots, in which you'll use type equals L. One of the main takeaways whenever you do make a plot is looking at the overall pattern and then any deviations from that pattern. So you'll want to describe the center, shape, and spread, which can involve whether it's symmetric or skewed, and outliers. Take special attention to these things. The descriptors of center are mean and median. The descriptors of spread or variability are range, quartiles, IQR, variance, and standard deviation. In orange again are the R commands to find these sort of things. Remember, you can use 5num. If you get confused about what 5num is giving you, type question mark 5num and it will tell you. You can also use the summary command to tell you this information. Box plot command to make a box plot. Random means individual outcomes that are uncertain, but there is a regular distribution of outcomes in the long term. You need to know about probability of random phenomenons and empirical or relative frequency probabilities. There are also personal or subjective probabilities. So for this and for any of the other things covered on this PowerPoint, what's important is that you should go and look at your professor's slides for the entire semester. Look through those, see what you should study, because those are a lot more detailed than the final review since it's just so much material to put into one review. So please just go look at your class R scripts and the PowerPoints from class. If any of these concepts sound unfamiliar, maybe you don't need to do that because you already understand them. Okay, so when looking at probability models, here are the things you should keep in mind. You need to know what sample spaces are, and you also need to know all the probability rules. For a lot of this stuff, especially probability, the best way to master is just to do as many examples as you can, and as I mentioned earlier, you can do the problems in the back of the textbook chapters. So here are the rules. And make sure you can identify discrete versus continuous models. So here are the additional rules for disjoint events, the general addition rule, multiplication rule, and the general multiplication rule. So this format is probability of B given A. Just memorize this so you know the format. In regard to the multiplication rule, multiply general multiplication rule P, A, or B. The way I like to think of this as a Venn diagram, you're subtracting the overlap so you can find the area. without double counting the area between A and B. When you examine relationships, you should pay attention to these different types of variables: explanatory and response, independent and dependent. So make sure you can identify all of these. When you do a scatter plot, you can do plot x comma y or plot y tilde x. Both work, but in either case, you'll need to pay attention to positive or negative association, outliers, and linear patterns. Make sure whenever you plot, the right thing is on each axis, and if you accidentally forget, you can just switch it up. That is, if you forget, if you have y comma x and it looks wrong, you know you need to reverse it. And remember, x is the explanatory, y is the response. So predictor and response variables. Correlation is R, and it measures the strength of a linear relationship. It's between negative and positive 1. The closer the absolute value is to 1, the stronger the correlation is. The sign only shows association. So negative is negative association, positive is positive association. R equals 1 or negative 1 only for perfect linear relationships. So in the real world, you won't really encounter these much. Also, as always, correlation does not imply cause and effect. This just means though you may see a relationship, it's not necessarily going to mean that x is causing y. It could mean that x and y are heavily associated, but there's a lurking variable that's misconstruing your ability to see the relationship. When you do a regression, we do the least squares regression. This is the line that minimizes the sum of the squared residuals. When you actually create this regression model, it's lm y tilde x. That's the format to create your linear model. Whenever you type in model after you create it, you get the regression coefficients and their interpretation. Well, you get the regression coefficients. You need to know their interpretation. So for example, y equals 2x. This means for every unit increase in x, you have an increase of 2 in y. And it's important to actually be able to apply this. So not just with x and y's, but get a real world example and interpret the coefficients. Another thing is r squared. You need to know what r squared is. You get it from squaring the correlation, but it's also on the output that you'll get in r. Here's more information on random variables. Their formulas for the mean, variance, and standard deviation. It's much easier to get them in R, like you do on your homeworks and in some of my previous videos where you're creating vectors to solve for these things. But it is important to look at these formulas so you understand conceptually what's going on. Also, you'll need to know how to get the expected value and the variance. Key takeaway here is that to get the variance and thus the standard deviation, x and y must be independent. This is a very common trick. So make sure they are independent. Here are some different types of trials you'll need to know: Bernoulli, binomial, and sample proportion. Let's walk through all of them. So in a Bernoulli trial, the expected value is p and the variance is p times 1 minus p. B is the number of successes from one trial and p is the probability of success. Binomial is a bit different because the expected value is np and the variance is np times 1 minus p. And sometimes you might see q as 1 minus p. That's how I like to think of it. P success, q failure. The probabilities of those things respectively. Sample proportion, p hat is x over n, which is the proportion of success. Or the way I like to think of it is the success rate if you have n independent trials, and p the probability of success. The expected of p hat is expected value x over n, and then the variance is the formula as follows. This is saying if you decide to study by reading the book, ignore uniform geometric and Poisson distributions. An important thing about binomial distributions is, one, we didn't calculate binomial probabilities, and two, the total number of observations is fixed in advance. So if you remember from your practice exam for test 2, I believe, It wanted to know which of the following were binomial distributions. And the key thing to remember here is it must be fixed in advance, the total number of observations. That is, you can't say, oh, it's binomial, how many trials it takes to find 10 people who do X. That's not fixed. You should say, we're doing 10 trials. I hope that makes sense. If not, look at an example and see if you can identify them from there. The outcomes of N for all observations are statistically independent, and each observation is a success or failure. Again, this doesn't mean it's literally a success or a failure. It's just the nomenclature for this type of thing. So the probability of success has to be the same. Just a little piece of helpful advice. When you're doing this sort of thing, keep in mind that there are lots of conditions for different types of distributions, different types of models. To keep them straight while you're studying, just write it down. Put it on your sheet. Have different sections on your sheet, one for binomial. And whenever a question about it pops up on the practice exam or the real exam, go back to your notes, because you'll get 3 pages, as I mentioned, and look at the conditions for that. Here's the normal distribution. So one of the things you need to look at first, or that we looked at first throughout the year, is the 68, 95, and 99.7 rule. This rule refers to that 68% are within 1 standard deviation, 95 within 2, and 99.7 within 3. Practically, this means it's pretty unlikely you'll find something outside of 2 standard deviations, and extremely unlikely you'll find something outside of 3 standard deviations. If they're standardized, the mean is 0 and the standard deviation is 1. For normal area calculations, you're going to be finding areas. This is what I mean. The p-norm returns a probability. The q-norm returns a value. And when p-norm finds the area, the probability, it's going to find the area to the left. So always draw a picture when you're solving these problems. Label your picture, and then if you're actually trying to find the area to the right, do 1 minus p-norm. As I mentioned, q-norm covers values from your probability. Whenever you're doing this, make sure you use HIST and QQ norm to make sure the data is normal. And for calculations about x bar, which is the sample mean, you use S over the square root of n for the standard deviation. Important thing to remember for this is number of successes in P and number of failures in 1 minus P are at least 10, with mean in P and standard deviation square root in PQ. Here are some different definitions. You can pause the video now if you would like to read over these. Okay, same with these big ideas. Sample examines a part of the whole. Randomization is to avoid bias. And the sample size matters. So here are different causes of bias. You may want to pause the video and see if you can correctly identify all these types of bias and identify examples of the bias. Some good examples are, again, on your homework. Okay, the sampling distribution of p hat. This is a really nice picture that describes some key things you need to know, also written below. This is an important dichotomy to make. P hat versus P. Make sure you understand that relationship, and P hat being a statistic and P being parameter. Okay, standard error is S over square root n. SD is typically unknown, so we estimate it with the sample standard deviation. The really big idea here that encapsulates the entire course is that we don't know about the population, so we are using samples and statistics to estimate things about the population. So keep that in mind. Don't miss the big idea because you're getting too concerned with the details. Details are important, but make sure you understand the big idea. Okay, now on to statistical inference, which is a method for drawing conclusions about the population from sample data. There are two methods for this, confidence intervals and tests of significance. We'll talk about both. So before you do inference, look at these four conditions. Independence, you want the sampled values to be independent. Randomization, you want the sample from a simple random sample from the relevant population. The 10% condition, the sample size is less than 10% of the population size, and the success failure condition. Again, if you want a lot more details on these, you should go to your instructor slides, and they're a lot more detailed than what we're going over right now. Here are specific conditions. In P hat and in Q hat are at least 10. In P null and in Q null are at least 10 if you're doing the hypothesis test for proportion. In CI and test for means, n is greater than both 10 times the squared skewness and 10 times the absolute value of kurtosis minus 3. Remember, if you're using skewness and kurtosis, you should install and use library for the package called moments. And here in orange are more regarding that. So a confidence interval has the form, the estimate plus or minus the margin of error. And this is the formula. So margin of error expanded is this. The really important takeaway from this for me that I like to think about is drawing the picture, right? Because I've seen some problems on these and it's really easy to get confused. I don't think the best way to go about this is memorizing all the relationships. I think it's memorizing the formula and then trying to modify the formula to see if you can infer the relationships about these. For example, if you increase Z star, you can see that your margin of error is going to get wider because they're directly related. So think about the impact of each thing on each other. The confidence level C shows how confident we are that the procedure will catch the true population parameter. The best way to think of this is just going to see all the examples, because this is exactly what the confidence interval means. But to me, it's kind of hard to understand from direct definitions. I really like seeing examples to make sure I can actually understand as best as I can. So here's the confidence level C, and it shows how confident we are that the procedure. So like I just said, confidence intervals, and we have different types of problems: proportions, means, matched pairs. Matched pairs are the same as means if you calculate the difference for each pair. So I believe on learning catalytics, you should have good examples of different types of problems you face with this, and you have two independent samples as well. So here's the confidence interval for population proportion. We have the estimate, standard error, critical value, margin of error. It's important to know what all of these are. It's really easy to get really caught up and figure out how to calculate these small things, but it's more important to conceptually understand why you're doing this and what these are. So you may want to pause right now and make sure you have all these formulas down. This goes how to find Z star. So these are the same thing. They both help you find Z star for a 95% confidence interval, and these are how you find Z star for a 99% confidence interval. So it's a bit different for confidence intervals for population mean. You're going to draw a contrast for population proportion P that I just went over, and then what I'm going to go over right now, the population mean. So compare and contrast. Estimate there, estimate here, and just go down and look at all the relationships and see how they're different. But one of the main things that's different is T star versus Z star. So if we're finding T star for the 95% confidence, we need to take degrees of freedom into account. So here we use Q norm with no degrees of freedom for Z star, but for T star we use QT, and we do need to have the degrees of freedom. So make sure you understand that, the difference between the two. Here's some about hypothesis testing. Here is the hypotheses. So what a hypothesis is you're stating a claim about something. And we have two of these. We have the null hypothesis and the alternative hypothesis. Make sure you can form examples of both and how they apply to not only hypothesis, just different kinds of hypothesis testing and including linear models, things like that. So make sure your conditions are satisfied. And make sure, again, as I mentioned earlier, you know the differences between these. Z and T are not the same thing. Okay, more on hypothesis testing here, really important information. The end result of your hypothesis test is you do all this work, you get a p-value, right? And that p-value will tell you like whether or not it's likely that you would have gotten the results you did given that the null hypothesis is true. So that's why you compare it to your alpha level or your significance level, which is typically 0.05, sometimes 0.1. If your p-value is lower than the alpha, you reject. If it's higher, you fail to reject. So as is more concisely written here, okay, there are different kinds of tests. One-tailed tests, you can have p greater or p less than, and then two-tailed tests. Here are representative pictures of how you find both. The actual commands you would use are shown. 1 minus p norm this or p norm the same thing. And to get for two-tailed, you double. Okay, so now continuing the contrast I drew earlier, this is the p-value for means. So this is a bit different. It's conceptually similar, but it is different conceptually and different in practice. So one-tailed test and alternative. Again, just write down these formulas or memorize them. Make sure you have them. And for two-tailed, not much to say besides know these formulas, how to use them. So R functions, as Dr. Greenberg wrote here, the ci.prop and ztest.p and all datasets are given in the R data file, similar to how it was given on the previous tests. So nothing new there. Don't worry, the format's not going to be extremely switched up or anything. And you can use the t-test function as I'm sure you've had lots of practice doing your project. Okay, so as we talked about before, scatter plots and correlation. Look out for all of these things. Now, we did talk about regression earlier, but we're talking about multiple regression. Well, you use element summary for your single regression, but you also use them for your multiple regression too. So let's create a little bit of contrast. So earlier I said y equals 2x, right? And as we mentioned, this isn't very hard to understand. You increase x by 1 unit, you increase y by 2 units. But it gets a bit more complicated if we have y equals x1 plus x2. Now if our coefficient for x1 is still 2x, the interpretation is different because y only increases 2 units for an increase in x1 by 1 if x2 stays the same. Okay? Your last homework will teach you more about that and help you actually apply those concepts. But a lot of from single to multiple regression, many things do stay the same. A really valuable tool to have in your tool belt for this test is confint, which you use it once you create your linear model, and then you create a confidence level you want to use, and it will give you your confidence interval for your regression coefficients. Very important to know. Hypothesis test for regression coefficients. Let me give you an example of this. So for your null hypothesis, you would say the slope of the for x1 is 0. That's for a single regression. For multiple regression, coefficient for x1 is 0 and coefficient for x2 is 0. And then your alternative would be that they're not. You could have it being a one-sided as well. Okay, so some assumptions: linear relationship, normal errors, and constant standard deviation and independence. So now we're going to go over how to determine if it fits the conditions. So you're plotting x against the residuals here, and here you're predicting values against residuals. Both are important plots to look at. If you're going to do this, you don't want any patterns. You don't want especially a fan or a cone. They can indicate it's not a linear relationship. And the cone or fan, I suppose, that's where it's kind of looks like a sideways V shape. And it just means that the prediction is less accurate at higher values of x. To look for normality, look at skewness and kurtosis, and also you could look at the histogram and normal quantile plot. So normal quantile plot QQ norm, histogram hist. You want constant standard deviation, so the residual plot not showing increasing scatter. And in regard to independence, it's satisfied for randomly selected cross-sectional data. So it looks like we've gone through all the slides. Again, thanks Dr. Greenberg for this PowerPoint. And it covered everything for the whole year. If you want more specifics about anything I mentioned, you should look at your instructor slides, like I've said. And if for some reason you still have a question, email your instructor, or you can email any of the TAs. Those emails are all listed on the respective syllabi for the classes. So I really hope this was helpful. Good luck on the exam. You can all do wonderfully.